How's it going? My name is Danny Allen, and for the past 2 semesters, I've been doing research with Professor Trushinsky on augmented reality, and I'm excited to share some of my findings. I've been doing this in parallel with my internship at Excavators and some of our recent endeavors with augmented reality as well. With the recent burst of activity in AR, especially with Google Glass in 2014 in regards to the consumer industry, most of the technical work has avoided mainstream media because they're targeted at enterprise systems. That being said, AR is still just passing its infancy, and we probably won't see much besides face filters and dancing emojis for 5 to 10 more years. It is, in my opinion, and that of many other experts, that consumer augmented reality could be the next paradigm shift since the internet and smartphones. So, a quick overview. I'll introduce AR, followed by a brief history, some of the current obstacles in the field, which leads into some of my research. Finally, we'll talk about making a meaningful experience with AR and a high-level overview of the software engineering we're doing at Expo. So before we go into the details, it is important that we kind of have a running definition of AR and its misunderstanding with virtual reality. On one end of the spectrum is augmented reality, which allows the user to see the real world with virtual objects superimposed or composited with the real world. On the other end is virtual reality, which is an entirely artificial environment provided by a system in which one's actions partially determine what happens in the environment. Mixed reality, however, takes the best of both of these. You can think of AR as simply overlaying digital content onto the real world, whereas mixed reality has virtual objects integrated into and responsive with the real world. So while the history of AR does go all the way back to 1968, it's really not until the 2000s when we'll start to see practical applications. But in 1968, however, Ivan Sutherland creates the first head-mounted display system. This system used computer-generated graphics to show users simple wireframe drawings. In 1974, Myron Kruger built an artificial laboratory called the Video Place. The Video Place combined projectors with video cameras that emitted on-screen silhouettes surrounding the users in an interactive environment. The term augmented reality was first used by Tom Caudle in 1990, and then in 1992, Louis Rosenberg developed virtual fixtures, one of the earliest functioning AR systems built for the Air Force.
Why does the first one count as AR?
The heads-up display is still overlaying onto the real world.
Okay, so even though it's like not interactive with the real world, you can still like see both at the same time?
Yeah, that's kind of the difference between AR and mixed reality. AR just puts it out there, whereas mixed reality makes it immersed into the real world, if that makes sense. He developed virtual fixtures in '92. It was one of the earliest functioning AR systems built for the Air Force. It was a full upper body exoskeleton, which allows the military to control virtually guided machinery to perform tasks from a remote operating space. So once it begins to pick up a little bit of steam, we'll start to see it in popular entertainment. The first and 10-line computer system is broadcast by Sports Vision, casting the first virtual first down marker during an NFL game live in 1998. In '99, naval researchers began working on Battlefield Augmented Reality System, the robust original model of early wearable units for soldiers. And a year later, Hirokazu Keidu created AR Toolkit, which was an open source software library that uses tracking to overlay computer graphics onto a video camera. This toolkit is still widely used to complement augmented reality experiences today. And then later in 2009, that same toolkit was brought augmented reality to web browsers. So finally, that'll bring us to today. In late 2013, car manufacturers began to use it as the new age vehicle service manuals. It was the Volkswagen Marta app, mobile augmented reality technical assistant. It provides virtual step-by-step repair guides for the technicians, allowing them to foresee how a repair process will look on the vehicle in front of them. And I included this one because this is pretty much precisely what we're doing over at Linkbo as well, but I'll get into that further in the presentation. In 2014, Google announces Google Glass. It was really the first consumer-oriented device. It started the trend of wearable AR. And then finally in 2016, AR and virtual reality reached $1.1 billion in investment, and Microsoft HoloLens developer kit is set to ship. The one thing I didn't add on this, HoloLens 2 was actually just announced about 2 to 3 weeks ago. So as I mentioned, I want to talk about these a little bit more because I'll reference them a few times throughout the presentation. Google Glass was 2014. Again, it was really just a heads-up display, but it had huge hype surrounding it. And then on the bottom right is HoloLens 2, and that's really the centerpiece for consumable AR at the moment. So in the field today, there's a number of obstacles facing augmented reality, but they can all be grouped into these 5 categories. The first and easiest to define would be limited hardware capabilities. Here we see a main problem with the field of vision, which is the total angular size of the virtual images visible to both eyes. For a healthy adult, the horizontal binocular overlap is 120 degrees, with a total field of view of about 200 degrees, and the vertical field of view is about 130 degrees. That being said, the current standard on hardware devices is the HoloLens 2, and it only has a horizontal field of view of 43 degrees and a vertical field of view of 29 degrees, giving it a 3:2 aspect ratio. While this is a massive improvement over previous devices, there's still a ton of room for improvement, and we're still quite a ways from actually fitting these into a pair of spectacles. A huge problem here is that we want to optimize the hardware. Engineers want to create the most robust systems, but you're also going to be wearing this on your heads, and the current headsets that are out there really limit you to no more than 30 minutes or so before it's lumbersome to keep on your head. Other than that, cell phones are also a poor medium for rendering 3D images, as the cameras are made for 2D capture. In terms of software issues, there's a number of useful frameworks out there for single user interfaces, but there's yet to be a robust system for multi-user experiences. Apple's ARKit and Google's AR Core do seem very promising, but it limits the scope of development, and we're failing to run AR on off-the-shelf devices, which are bigger than mobile and tablet. I don't know if all of you remember when Google Glass was first announced. The hype surrounding it was also part of its demise. It became so extreme that we ended up expecting too much, which was similar to the augmented reality industry in general. Looking back at the Gartner hype cycle, we see it reach its peak of inflated expectations right around 2014, and then we don't hear much about it for a few years as it was going through the trough of disillusionment. And as of 2018, it sits about halfway up the slope of enlightenment, and it's still about 5 to 10 more years before we'll see it reach the plateau of productivity. Uncomfortable architecture is just a messy concept that is combining the real and virtual worlds. Even more so, if we think about it, computers, television, phones, they all give us some sort of health issue. We're certainly a lot less active, and digital unplugging has really become somewhat of a trend these days, and it certainly won't get any better if we're outfitted with powerful glasses. And like most emerging technologies, AR will take a lot of time to become widely accepted by the masses. Whether that's from ethical issues or functionality concerns, this is why companies today need to keep long-term vision ahead of short-term ROI. Speaking of ethics, it's actually a really interesting and mostly unanswered topic in AR. One of the main reasons Google Glass failed years ago was for privacy issues. There were major concerns that it invaded bystanders' privacy because the device could record anything the user wanted. Along with the privacy lines, we are already being flooded with ads in the real world, whether on social media or anywhere else an ad banner could fit on your device. If we all had AR headsets on, advertisers could literally control our field of view with pop-ups and notifications. Google's AR Core has an app called Just Align, which lets users draw in spaces in AR and then share those drawings with their friends. It seems harmless, but this is the internet, and it's easy to imagine a world where this gets more popular and you can't walk down the street without looking at a building without seeing harmful graffiti. And because the graffiti isn't real, it's almost more dangerous. We can confront things that are out in the open, but things are only visible to a handful of people in the augmented world, and we have little hope of stopping them. Finally, property rights in the virtual world will have to be governed as well. If AR ads are projected in your home, what are your rights if you want to take them down? Conversely, could you theoretically sell your blank spaces as territory for AR ads? What if you only want to show some but not others? Will huge companies outbid smaller players for this privilege, returning us to the status quo? There's actually a new company called Versus that's trying to do just this. They call it the Smart World platform, and they're trying to offer spatial domains, which are the protocols and standards for the next generation of the web. And then Pokemon Go was a sensation about 2 years ago, and it had to grapple with just these problems. For those of you who are unaware, it was a massively popular game where players had to physically travel around to catch and battle Pokemon. But because you were traveling around, there were people playing games at memorials and cemeteries and in the middle of busy roads. So they solved this by geofencing certain areas where the game wouldn't work. And that was a good solution, but it is a huge indicator of what's to come. So as much as I'd like to discuss one paper for every area of research in AR, I really only have time to discuss one. That being said, the heaviest areas from researchers are in field of vision and device size on the hardware side, and occlusion, user-defined hand gestures, and multi-user experiences on the software side. So the paper I'll talk about was from 2010 UKY-Computer Society Conference on Computer Vision and Pattern Recognition, and it was by Stephen Gameter, Alex Gassman, Lucas Bossard, and it was out of the University of Zurich in Switzerland. The objective was to present a system for mobile augmented reality based on visual recognition. They split the task of recognizing an object and tracking it on the user screen into a server-side and a client-side task respectively. This hybrid approach was tested on a prototype Android application, which was able to augment stationary landmarks. The database on the server side consisted of hundreds of thousands of landmarks, which are crawled using a state-of-the-art mining method for community photo collection. In order to fulfill the real-time constraints for AR application, they also introduced a method to speed up geometric verification of feature matches. Finally, they introduced a motion estimation method, which is more efficient and precise than similar approaches. There have been two major improvements that led to this. The first was in computer vision, which has made huge progress in visual object recognition, both in terms of precision and scalability. This coupled with methods for retrieving specific objects from databases with millions upon millions of items in a matter of seconds. And the second was in smartphones, which can build artificial markers in order to track objects. Combining these two has the potential for some really exciting AR applications. So the application worked like this. The tracker on the client initiates a request to a recognition service, transmitting a frame grabbed from the camera feed over an HTTP connection. The moment for sending this request is based on a heuristic in the tracking algorithm. The service response will consist of XML data containing the information about the recognized object and the location of detection in the query frame. These bounding box coordinates are then used by the client to reinitialize the tracker, and the title is used to label the augmentation on the screen. In terms of the landmark recognition on the server side, they need to collect a sufficient amount of images for a large number of landmarks from around the world. To do this, they crawled geotagged images from Flickr, and all photos which were geographically close to each other were then also checked for some similarity and clustered together, which is seen there. For all images in the cluster database, their features are quantized using a visual vocabulary. For every incoming query image, the same procedure is applied. The query set of visual words is matched against all database visual word sets using the intersection as a distance measure. The efficiency here is obtained by using an inverted file structure. For the closest 500 candidate images, a geometric consistency check is performed. This is done by means of an estimation of the homography mapping of features matching between the query and the database candidate. The final step is then a voting procedure where the retrieved database images vote for their clusters, and the cluster which receives the most votes will win. This geometric verification step turned out to be the bottleneck for achieving AR-compatible response times. If we assume that a single file access takes 5 milliseconds, geometric verification alone would take at least 5 seconds. To combat this, the images are compressed using a product quantizer in order to be able to keep the features in memory. The main idea is to decompose the feature space into Cartesian products of low-dimensional subspaces and to quantize each subspace separately. A feature vector is then represented by a short code composed of its subspace quantization indices. In their implementation, the entire 64-dimensional feature space is quantized using only 8 centroids. Then, for every feature vector in the training set, we subtract its closest centroid, and the marginalized features are used to train a product quantizer. To that end, we divide the 64-dimensional feature space into 16 4-dimensional subspaces and quantize features in each subspace using k-means with 1024 centroids. Thus, a feature vector is now represented by a compact 160 plus 3-bit code instead of 64-bit integer values. Using this method, they reduce the size of 1 million images from 300 gigabytes to 30 gigabytes. In the original implementation, geometric verification is performed using uncompressed feature files that are loaded from the disk. The resulting recognition times would be on the order of 10 seconds, which isn't sufficient for AR applications. Using their in-memory quantized features, we achieve recognition times strictly under 2 seconds. When they handle the actual implementation of the code, they use Java for network and sensor handling. However, for the visual tracking, they had to resort to native code in order to allow for interaction with frame rates. Frames are passed from Java to native C code, which handles feature extraction, feature matching, and motion estimation. In the end, they demonstrated a fully functional and complete AR system, which recognizes and tracks stationary as well as mobile objects. It combines a client-side implementation on an Android-powered mobile phone with a server-side object recognition service. The client-side application allows for real-time tracking and interactive usage. The server side provides AR-compatible object recognition service for 3 million object clusters with response time strictly under 2 seconds with a memory-efficient geometric verification. In the whole setup, they don't use any markers and do not require any GPS information for object recognition and tracking. So keeping all this in mind, when I graduate, I'll be going into a software engineering role and not as much an academic research position. That's why understanding how to make a meaningful AR experience has been some of the most important research I've done these 2 semesters. All too often, we see gimmicky AR experiences that only provide value the first time you interact with it. It's so important to consider what augmented reality actually adds to your device. The application, if it relies only on virtual objects, it tends to be better suited for virtual reality. Conversely, sometimes AR is added just because it's AR, which actually means it's better suited as just a mobile device. It was Jack Dorsey, the founder of Twitter and CEO of Square, that said the best technologies disappear. They fade into the background and they're relevant when you want to use them, and they get out of the way when they don't. Keeping this in mind is one of the most important principles of augmented reality engineering. So when creating an AR, there's 3 principles that it must adhere to. It must combine the real and virtual, it has to interact in real time, and it is registered in 3 dimensions. However, none of these address the concept that it must be immersive for the user. The program must work with the user as the center of focus, and multiple senses must be considered. Take this simple example. Imagine a lamp appearing virtually in front of you. It's impressive, but it really provides no context. Now imagine the lamp appearing in front of you just at the right time when you need more light, or it shuts itself down when it's time to go to bed or leave for work. This now provides substance to an otherwise unnecessary event. To further illustrate this, we compare augmented reality to the attractions of the first cinemas in the 1900s. In the beginning, customers were excited just to see moving pictures on screens. But once that fascination was gone, the movie studios had to actually focus on the content of what they were making. This is the same that's happening in augmented reality, and we have to create some level of context to keep the users immersed. To actually do this, there's 4 general guidelines. The first is don't lose the plot, start with the story. A captivating narrative is the core building block of any engaging AR experience. Think of it as a blueprint to a finished house. The story provides the framework that decides the depth and the scope of your project, as well as the components needed to bring the story to life. Using the technology as the starting point can lead to delays, confusion, and even an end product that doesn't quite fit the purpose. Consider whether AR is the right tool in the first place. Building for laziness assumes that if the experience gets too abstract or hard to figure out, the users will switch off. There always needs to be a clear goal and method of progress towards it, or else fun can quickly become a frustration. Creating cues as subtle as faintly highlighting an object of interest with an action prompt that appears when you're in proximity of it, or it's just a way to direct the user's attention using features within the parameters of the environment. A multi-sensory approach often works best. For instance, you can add a hum that increases in volume the closer you get to a highlighted object, or a section of narration that hints at what to do when interacting with an object. Finally, an easy immersion technique is to gamify the experience. The addition of points, collectibles, and tangible progress might seem small, but it can add an entire layer of depth. Bonus points if you're able to add cooperation and competition. So to wrap up, I wanted to share some of the augmented reality I've been doing over at Linkbelt. I have to keep it at a high level because that's all I'm allowed to talk about. But for those of you who don't know, Linkbelt Excavators is here in Lexington, and I'm sure you can guess it, but we make excavators. And keeping in line with our 5 and 10-year plans, we have many ambitious aspirations for incorporating augmented reality into multiple facets of our business. Those 3 to start with are virtual training, marketing gimmicks, and remote collaboration. One of the biggest problems in our industry is the shortage of service technicians. Young people no longer aspire to be a service tech, and the older generation is all retiring. That's why it's important to bring this technology in as a way to recruit new techs as well. So, with regards to virtual training, the overall concept is overlaying virtual objects on top of excavator components as a way to expedite the training process and provide a resource for techs to use as a refresher or a lifeline out in the field. It provides step-by-step assistance on how to fix or maintain a problem. It would even virtually overlay what tool to use and how to use it directly onto the component. We're also partnering with Microsoft to bring this to HoloLens as a hands-free option for technicians. Earlier, the research paper I discussed involved separating the server and client-side tasks. We're actually doing this exact technique. All the manuals and parts pages for each excavator makes for a huge amount of data, much larger than the storage capacity of these devices. So we have to send all the object recognition to the server side. It's important to note that the ability to view models is not a new idea at all. In fact, it dates back decades. What's different here is that it's merging together the real and digital worlds in a seamless fashion.
I have a question.
Yes?
Is like the main purpose of the AR technician stuff to like reduce the amount of skill it takes to become a technician?
Yes, and reduce the amount of time it takes to complete one of these fixes, exactly. So doing all this research with engineering, along with the stuff I've done at Linkbelt, it's kind of helped me find my passion in computer science, and especially for augmented reality. And I think in the next 5 to 10 years, we'll start seeing consumer-oriented devices. So if you have any questions, I'd be happy to answer them.
So what applications are there besides helping train someone to be a technician? I can't imagine it around the house, what I would use augmented reality for.
Well, one thing to consider, when they announced HoloLens 2 just a few weeks ago, they announced it at the Mobile World Conference, which, I don't know if you know that conference, but it's traditionally for smartphones. And Microsoft has been absent from it for 10 years since they stopped doing the Windows Phone. But the head of HoloLens, Alex Kipman, it's his thought, and really a lot of people thought, that these headsets will ultimately take over your smartphone, and you wouldn't even need that at all. So everything your smartphone could do would eventually just go to a hands-free wearable.
So I could read mail, for example, while eating breakfast.
Absolutely.
I would see both
And nobody would know that you are doing.
right, I would
Yeah.
see the breakfast, but then overlaid on it might be comic strip news.
Yeah.
Okay.
There's actually one really cool company. They're making photorealistic food for restaurants to use. So you'll pull out your phone at a restaurant, say you want to order, I don't know, a steak, and you'll get a photorealistic image of a steak and the sides that come right onto your table.
You can't eat it.
No, you can try. Yes?
So how have things changed since, I think, Oculus Rift, was Oculus Rift the very first VR
Yes.
device, and how, and is Oculus Rift still out there? And how are things kind of merging, I guess, between those two areas? AR and VR.
Eventually, a lot of people see VR and AR merging together. So right now, the headsets are completely transparent, but there will probably be a way one day to completely occlude that field of view. and you can do anything in virtual reality that you could also do in AR. But I definitely don't know as much about VR as I do AR. Yes?
In terms of the human interaction of just like hand motions, how does your research?
So we actually just discussed a paper a couple of weeks about this, and they also talked about it in the HoloLens demonstration. In HoloLens V1, everything you had to do was with this unintuitive click with your fingers. Now all the new devices have full hand tracking, so you don't have to do some weird maneuver to make something work. If you see an object, you can grab it and scale it just as you naturally would.
And that's being done by the function, correct?
Yeah, they're doing that as well.
Who's heading up, like, who's leading
Who's ahead of Magic Leap, or who's ahead between of Magic Leap and Microsoft?
not in, just so like which group is like Microsoft?
Oh, Microsoft by a huge margin.
Yeah.
When Magic Leap put out their first device, it was only on par with HoloLens 1, which had come out 4 years earlier. Yeah. So now HoloLens 2 is out, and it blows it out of the water. We're partnering with them, yeah. Yes.
A lot of these devices handle focusing problems. I'm looking out at the world and I'm focused at infinity.
Mm-hmm.
This device is going to be showing things which are really focused at 6 inches from my eyes. How does that work?
Well, we can also put objects that appear further out as well. It doesn't always appear right in front of your eye. That's part of the immersion.
So it's possible to project something onto the screen that looks like it's actually focused at infinity?
Yes.
That surprises me. I had no idea how you could do that, though. I believe you.
On a lot of devices, before you have to use it, you have to scan the entire room. So then it'll understand the geometry of the room, and it'll decide where to put things from there.
You can hold a mirror right in front of your face and focus different lights.
Yeah, but you can't simultaneously be looking at something that's as close and far. Your eyes can adjust to pretty quickly between one and the other, but it's no longer immersive if I'm trying to put an arrow on something which is really 20 feet away. But the arrow is actually physically only 6 inches from my eyes. How do I make it look so that the arrow is actually focused out at 20 feet and the thing is pointing at?
I actually don't know exactly how they do that.
It's
Yeah.
waveguide, so the light is effectively, you project it as if it was like everything 15 years, maybe in moments. So effectively, the light is focused at very far distance.
Okay.
It's pretty impressive. I haven't had it clean one shot.
Microsoft's interested at all in eye motion tracking?
They have that in HoloLens too. They have full eye tracking.
So it will now focus, like the image actually focuses.
Yep.
Well, it's all magic. So stay tuned for next week's Keeping Current, and thank you very much.